So the topic for today is going to be greedy algorithms. That's a very important class of algorithms that we should learn in an algorithms course. And what I'm going to do maybe for the next 2 or 3 lectures is to give you multiple examples of greedy algorithms, show you the analyses, so that you have some idea of how greedy algorithms work. So let me begin by projecting my screen. All right, so greedy algorithms. And again, you should really think of this as done for, we will think of discrete optimization problems. The same setting for dynamic programs. So typically what we have is we have some function and we have some function on, I'm just going to use the Boolean, although it could be much more than that, to R. So this is our set of objects represented as strings. As Boolean strings. And our aim is typically to do some kind of min of every subset of n of f of s, or min, or maybe you want to maximize over all subsets of s. So in dynamic programming, what you do is, you design a recurrence using using some sort of what I'll call optimal substructure. And what you say is, to solve a problem, you need to solve smaller versions of another problem. Then you observe overlapping subproblems, and then you fill out a dynamic programming table. Now, one of the things that I will say here is, in some sense, coming up with an algorithm is hard. Like, you really have to think carefully about, you have to think about the recurrence, you have to observe this. So coming up with the algorithm is hard. The analysis is easy. What I mean is that once you come up with this, the proof of correctness is almost obvious. The proof of correctness is almost obvious. It's obvious because of the recurrence. Now, greedy algorithms and the other thing over here is there is this bottom-up feature, although you can do memoization, but really I'd say the right way to think about dynamic programming is bottom-up. Greedy algorithms are more of top-down. So what greedy algorithms do is, so I'm just going to mute everyone. All right. So in a greedy algorithm, we will construct the set S, which is the one that the optimizer incrementally by making the best choice at each step. We will make the best choice at each step. So coming up with the algorithm is going to be easy. But the analysis is hard. And I want you to sort of keep this in mind, because the analysis of a greedy algorithm is not so obvious. Although to come up with the algorithm will be relatively straightforward. Okay, so enough of sort of philosophizing. Let's go ahead and let's start with a problem. And what we will look at is, again, we will look at the knapsack problem. Knapsack problem with what I'll call fractional weights. So remember, what was the setting of the knapsack problem? We have W, which is the capacity of the knapsack. And then we have items. The items will be 1 to n. And so I'll just use subscript notation over here. So Vi is the value of item I, and Wi is the weight of item I, right? So you remember, this is the setting of the knapsack problem. Now here's the twist. Previously, when we did knapsack, so what we actually did was what was called the 0-1 knapsack. You pick a subset of items. In the fractional knapsack, you can pick a fraction of an item. Okay? What this means is you can decide to take half of the ith item, in which case you're going to get a value which is half, but a weight that's half. So think of these as continuous. Instead of thinking of the objects as discrete, you can think of the object itself as continuous. So sometimes it's thought of as like maybe it's a liquid or it's some kind of commodity, and you get to pick, you get to decide how much you want of that commodity. What you have is a weight, and you have the total weight and the total value of an item. Does that make sense? So here's your item, where value, weight, value, weight, value, weight, so on and so forth. So instead of picking the entire item, you can decide to take some part of this, some part of that, some part of this, and some part of that. So the problem is, sort of find values. So I'm going to choose a fraction for each. So I'll call it alpha 1 to alpha n, such that for all I, alpha I is between 0 and 1. It means I can take none of it, I can take all of it, or I can take some portion of it, such that the total weight, so what is the total weight going to be?
W.
What is the total weight of the items that you picked? So let's say you picked alpha 1 of the first, alpha 2 of the second, so on and so forth. Think of this as a continuous item, right? So you get alpha I wi, and this has to be less than w. What you want to do is maximize of I going from 1 to n of alpha I vi. Because the value in 0-1 knapsack, the alphas have to be 0 or 1. In the fractional, you can pick a real number. So fractional, 0-1 knapsack means that alpha is either 0 or 1. Whereas in the fractional version, alpha I can be between 0 or 1. Does this make sense? Does the question make sense?
If it's fractional, why wouldn't the weight always be W then at the end? And we just want to if we just want to maximize the total value, wouldn't we always want to get up to W? Not less.
That's a good point. So technically, what could happen is if the total weight of everything was strictly smaller than W, then you will just take everything in one go. But your total weight is not going to be W. Does that make sense? So suppose it turned out that the summation of Wi was actually strictly smaller than W. In this case, of course, the problem is trivial. But nonetheless, I want to state something formally so that it holds for all situations. What you can argue is that when the weight of the knapsack is less than the total weight of the items, you will always fill up your knapsack. Does that answer your question?
Yeah, it does. Thank you.
This is just to be formal. I've written it this way. Otherwise, I have to make an assumption that the summation of weights is, which you can also do. But I also wrote it like this for another reason, which is I wanted to show you that the fractional version and the continuous version are sort of related. It's just by changing the constraints on the alphas, but you still have the same formulation, right? Whereas if you gave the formulation where it's equal, then you wouldn't be able to do the 0-1 version in this way. Okay, so how do we solve this problem? The algorithm is much easier. There's no table, there's nothing. What is the first item you should pick? Just think about that.
The one with the best cost to weight ratio.
Best cost to weight ratio. So, or rather value to weight, right? So you want to maximize. So pick the item with the highest value divided by weight ratio. And so you pick the item with the highest value to weight ratio. So what you can do is, and how much of it you take as much of it as you can. And then you move on to the next item. And then you take as much of it as you can. So what you do is, you can instead think of, let's sort items by the value divided by weight. Okay? So I'm just going to say this is going to give you the ordering pi 1, pi 2 to pi n. So pi is just the permutation giving the ordering. What you want to do is, just to show you a picture. Now this is the object, pi 1, pi 2, pi n. So I just relabeled things. You're going to keep picking this item. So you're going to pick as much of it until you either fill up your knapsack or you just take the item completely. Then you move on to the next one. And you keep taking it until you either fill up your knapsack or you get all of it, so on and so forth. Until maybe once you get to about pi k, you've just taken some portion of this. And at this point, the total weight of all of that will be W. Does the algorithm make sense? I mean, I'll write it down formally, but does the idea make sense? Questions? You see that the algorithm is easy to come up with. The proof, you have to think a little bit. We will do the proof. Any questions about this? So why don't we just write out process. So I'm just going to, hopefully I can fit it all in here. I'll just say initially the knapsack weight is 0. And then I'll just say for I, for I going from 1 to n, what I'll do is, remember, I've already sorted by this. So maybe I should, okay, let me maybe write this properly. Sorry. So step 1 is to sort items by wi by vi by wi. Let the permutation of the sorted order be pi. We'll just initialize. I'll say the knapsack weight, I'm just going to initialize as 0. And then I just loop through the elements for I going from 1 to n. So now what I do is initialize knapsack to be 0. I'll set alpha I, which is how much I'm going to pick the ith item, to be let's see, it's the min of, so either I take all of it or I take whatever is left in the knapsack, which is W minus the knapsack weight. All right, so I just set alpha I to be that. I set the knapsack weight to be whatever it was before, plus alpha I. I should initialize all alpha I to 0. And then if the knapsack weight is equal to W, then just return. Okay, so this is the algorithm.
Wait a second.
I'm sorry?
The weight should be alpha I times Wi?
Alpha I times Wi, I'm sorry.
Wait, shouldn't we be minimizing?
We should be, yeah, okay, so let me see if I get this right. So I have to divide. Okay, so I'm fudging something here. So I have to choose alpha so that it is this divided by Wi. Right? Because as long as alpha I Wi, that is the total weight of that object. And if that is less than what is remaining in the knapsack, I go ahead and take it. Otherwise, okay, good. Okay, right? So this is the knapsack, right? So this is basically just saying that when you look at the ith item, if you chose alpha I, the weight is alpha I Wi. So if the total weight is less than what is left in the knapsack, then you just go ahead and you just take it, you make it 1. I'm sorry, if the total weight is less than what is in the knapsack, then you just take the appropriate fractional. Otherwise, you just set it to be 1. Okay, and then you update your knapsack weight and go ahead. Okay, so what is the running time of this algorithm?
N log n.
N log n, right? Because you sort. So it's an O of n log n time. So how do you prove it's correct? How do we prove that it's correct?
You would have to prove A, B, and C. I guess like through a loop invariant.
Maybe showing like that there isn't another, like that any other, like assume towards a contradiction that there's a knapsack with more, that gives you more value.
Yeah, so you have to basically, so this is where, the proof is a little bit trickier. You have to think a little bit more carefully. So how does the proof go? The proof strategy is, so you consider an algorithm or instead of an algorithm, say consider an output that deviates from the greedy strategy. Consider an output that deviates from the greedy strategy. So you could always sort, and you could say, let's say alpha I is the output of our algorithm, let beta I be the output of the optimal. And let's look at where alpha I and beta I are different. And based on that, argue that if there's any difference, then that output must have a smaller value. So if you consider an output that deviates from the greedy strategy, argue that the objective value, and so what is the objective value? The objective value is this is the objective value here, right? Maximizing that quantity. So argue that the objective value must be smaller. Okay, this is going to be our strategy. Once you sort of put it out in that form, then the proof is easier to do. So let me now just prove the claim is the greedy algorithm outputs the optimal solution for this problem, right? For fractional knapsack. Okay. So what is the proof? So I'm just going to do for convenience. Let us relabel the items so that V1 by W1 is greater than or equal to V2 by W2, V3 by W3, so on and so forth. Let us assume all these values are distinct. This is just going to simplify the proof. It's you could assume that they have the same values, but then those items become equivalent. So we can assume these are all strictly decreasing. Okay. Now denote the greedy output by alpha 1, alpha 2 to alpha n. denote the optimal output by beta 1, beta 2, up to beta n. When you don't make this assumption, the proof is going to be a bit more, it's a bit hairier. And I can talk a little bit about this later, but let's start with this. Okay, now how are we going to make the argument? What we want to argue is that okay, and so now we'll say, suppose the optimal has a strictly larger objective than the greedy. How are we going to argue? Argue things. Any thoughts? Okay, can someone give me some properties of the greedy output? There's something about, if you think about the greedy algorithm and think about what the alphas are, the alphas satisfy a particular property. What is that?
They're decreasing.
They're strictly
Like almost all of them are 1, and
Okay.
then one of them is smaller than 1.
Okay, so the greedy output is basically, you have a bunch of 1s, then you have something less than 1, and then you have all 0s. Right? Because that's what the greedy does, right? Anytime it finds something that is less than 1, it's actually going to terminate. Because at that point, it has filled up the knapsack. If it ever terminates it not taking the entire item, then at that point it will terminate. Otherwise, if it can actually take everything, it means the knapsack probably has some more capacity left. Does that make sense? Any questions? So I'll draw this just draw it as a picture so that you see. So I'll say there exists an item I such that for all j strictly less than I, alpha j is equal to 1, and for all j strictly greater than I, alpha j is 0. This is just saying that if you look at what greedy does, it basically, there's some item, there are all 1s here, all 0s here, and this is alpha I, which may be, which is whatever. It may be 1, it may be 0, it could be anything in between. But otherwise, you have all 1s and all 0s. Is this property clear? Okay. Now, furthermore, what we know is, okay, I will make some simplifying assumptions in the proof just to sort of get things, make things easier. We'll assume that the summation of all the weights, and this is strictly greater than W. Because if that's less than W, then it's obvious, right? So we can assume that that's going to be more than W. So what this means over here is that we know that the summation of Wj, j less than I, plus alpha I Wi, this is equal to capital W. Right? Because this is just saying that you've filled up your knapsack, and that's what you filled up your knapsack with. Because we also know that the greedy algorithm always fills up the knapsack. The greedy algorithm always fills up the knapsack. Now, what we know is that the optimal output is different. The optimal output is different. So let I star, actually I star is going to look a little ugly. So let k be the smallest index such that beta k is not equal to alpha k. Right, this is just saying, so here's your alpha vector, and here's your beta vector. Somewhere beta has to be different from alpha. Right? Somewhere it's going to be different. So we'll say case 1. K is strictly smaller than I. So K is somewhere over here. So this is K. Right? All of these must be 1. Why are all of these 1? Why is everything less than that 1?
Because K is the smallest index.
Because K is the smallest index, right? I'm assuming it's the smallest index. So everything less than that is 1. So what do we know? We know that beta k is actually strictly less than 1, which is equal to alpha k. Okay, so now where's the contradiction? Where's the contradiction?
Is it when k equals I?
No, so there has to be a contradiction in this case, right? Because this is saying when k is less than I, you want to get a contradiction to the fact that optimal actually has a strictly larger objective. This is what you're contradicting. Optimal has a strictly larger objective. We need to contradict that. So we need to argue that somehow the optimal strategy actually made a bad choice. Why?
Intuitively, it's because you can just like, because that extra amount of weight was used to purchase items that are less cost effective. But like, I don't really know how to say that exactly in math.
Right. So what you're saying is, look, I mean, in this item, the optimal decided to take less of that item. So it's potentially taken more of some other item down here. Right? It took less of this, so it took more of something else. But if it decided to swap those, it could improve its objective, and that's a contradiction because it's the optimal. I'm going to say this again. I'm going to sort of draw a picture here. Right? I'm looking at the allocation of beta. Okay, so this is going 1, it took everything. 2, it took everything. So think of this being 1, taking everything, right? All the way up to k minus 1, it took everything. Here it took something less. Here it took something less. Now what we know is if there was any other item here where it took anything non-zero, it could actually, instead of taking that, take more of this, and it would improve its objective. And that would be a contradiction because it's the optimal. Hence, that means that there cannot be anything else. But then you can argue that whatever it's taken so far is strictly less than W, and you can again take something more. Okay, am I making some sense here? Do you see that there is something that you can show that there's a way of trading it off? You can say, well, if there's something else out there, then instead of taking that object, you could just take a little bit more of this object and you would increase your objective. let me write this out. The value of the optimal, it's summation of j strictly less than k. It's just taken everything here, so it got the value, plus the summation of j greater than or equal to k of beta j vj. That's the value of the optimal. Now, beta k is strictly less than 1. Now, suppose there is some, I'll call it k prime greater than k, such that beta of k prime is strictly greater than 0. This is your k prime here. Now, what are you going to do? And you also know the value of the optimal is this. We also know that the summation of, I'm sure this would be j, wj, j less than k, plus beta of j, wj, we know this is equal to w. You can argue that the optimal actually has to take everything. Okay. I mean, intuitively the proof makes sense, but when you write the math, I think it's going to give you some amount of clarity. Okay, so can someone, okay, Hazard, how are we going to get the math to work now? What are we going to argue? Suppose there is some k prime greater than k, so that beta k prime is greater than 0. How do I get my contradiction? How do I get my contradiction to optimality?
Put as much of that additional weight as you can onto beta k.
Put some of that additional. Okay, so now let's do the math then. Suppose there is beta k prime. How much?
Why does it have to be bigger than k? Can't it also put some additional weight onto k?
I'm sorry, which is bigger than k?
I'm saying k prime.
K prime. No, because
it doesn't have to be.
It has to be bigger than k, right? Because what do you mean?
Well, I'm saying that the optimal solution, or this version of the optimal solution, could be missing some on 2 but have more on k and not have k prime.
No, but this was chosen to be the minimum index. This is the smallest index where it's not equal to alpha, and therefore
sorry, I'm messing up k and I. I'm mixing them up.
Yeah, sorry. K and I are different. I is really with respect to alpha. K is beta's thing. Okay, so let's work this proof out. So what do you want to do? You want to take some weight away from k, and you want to put that on. I'm sorry, take some weight from k prime and put it onto k. How much should you take? You can actually just take any infinitesimal amount. You can take any infinitesimal amount. Okay, so you have to be a little careful here because you don't want to. You do not want to. You don't want to put more than the knapsack weight. You have to be a little careful here. So what you're going to do is, you could say, choose a delta greater than 0. Right? So you choose some delta greater than 0 so that whatever weight that you take away from here can be put over there, such that Okay, so this is, I mean, it's basically a continuity argument, but it's useful to see it in this form, such that delta is less than equal to beta k prime. And if you take away some weight from here, so you take away delta times the weight of k prime, like that's the weight that you're going to remove, how much are you going to put over there? You're going to look at wk. That is the weight that you're going to put back. That is the weight that you're going to put back. And this has to be less than whatever remains over there, right? So this has to be less than 1 minus beta k. Am I making sense here? Because this is how much of that, of the kth item you can afford to put back. Because you took away something from k prime and you're putting it into k. So when you take away delta units from k prime, the total weight of that is delta times wk prime. That is the weight that you removed. Now when you transfer it to k, the amount of mass that, the amount of the fraction of the item that you get is the total weight divided by, the weight of this object over here. So you have to choose something that has that property. You can argue that something always exists. There always exists a delta prime satisfying these properties. And now I consider the solution. I'll call this beta star, where beta star of k is going to be beta of k. Let me see if I'm doing this correctly. Sure, right. wk and beta k prime star is equal to beta k prime minus delta, and others are the same, meaning that beta of L is equal to beta star of L not equal to k prime. Does this make sense? So I modified it by doing this process. So I changed the solution in this way. Now I need to argue that this solution satisfies both of these constraints, because if it satisfies the second constraint, then it's a valid knapsack solution, and then argue that it actually has a larger optimal. Is this making sense here? Any questions about this? Any questions about this? It's a little hard to judge whether people are following or not, so I am going to poll you. Question is, are you following? A is yes, B is no. A is yes, I follow. B is no, I do not follow. Okay, so it's, there seems to be a reasonable cohort of people who are not following. So, someone asked me some questions.
Question?
Go ahead.
Hi, sorry. So, I'm a bit confused by your notations. You say that let's choose a delta, and then you subscript it, or are you multiplying it by wk prime?
Multiplying, right? It's not a subscript. It's multiplying.
Okay. It makes much more sense.
Yeah, because you're taking like a delta fraction of one object. You want to reduce k prime by a delta fraction. You want to increase k by some fraction.
Yeah, I understood that the writing confused me.
I'm sorry. Okay.
Like I thought I was a subscript. No.
Yeah, and you realize that you're increasing it exactly so that the total weight is going to be balanced out.
Yes.
Right? The total weight is going to be exactly the same as before, and therefore the total weight gets preserved, but the value is actually going to increase. The value is going to go up, and this is the key. Questions? Let's step back, right? If people are like, you want to, I don't know, so poll again, sort of, raise of hands. Do you want me to go over the high-level proof again? A is yes, B is no. Like go over from the beginning and tell you what is going on. A is yes, B is no. All right, there are enough students who would like me to go over the entire thing again. All right, so let's go back. What are we trying to achieve here, right? Let's go all the way back to the beginning. The greedy output is alpha 1, alpha 2 to alpha n. The optimal output is beta 1, beta 2 to beta n. What we want to argue is that the greedy output is actually the optimal output. So we're going to do it by contradiction. We'll say, suppose the optimal output was able to beat greedy. The optimal had a strictly larger objective than greedy. That means the greedy algorithm was wrong. Let us prove a contradiction to this fact. How are we going to do this? We are going to see where beta deviates from alpha. And we'll see that whenever beta deviates from alpha, it actually made a bad choice, and we can fix that choice and increase the value of the optimal. But that, that's a contradiction because the optimal is the best. Okay? So how do we do that? Well, let's look at the structure of the greedy solution, and this is key. So the greedy solution has ones in the beginning, then something which may or may not be one, and then all zeros. Right? Because that is how the greedy strategy worked. It sorted everything and it decided to pick a bunch of items, and then it sort of picked some item fractionally, and that was that. So the first time there is something that is fractional, everything else is zero. So this is what the greedy strategy does. What do we know about the greedy strategy? The total weight, summation wj plus alpha I wi, this is w. This is the total weight. Now let's look at the optimal. Now suppose the optimal output is different. So the optimal output behaved differently from greedy. There must be some index where it made a difference. K is that index. K is not I. K could be less than I, could be more than I, it could be anything else. We'll see that it cannot be more than I. K, okay, so this, I hope this is clear. K is an index where beta differs from alpha. This is where the optimal is doing something that is not greedy. We are going to argue in that case that there is optimal actually made a wrong choice. We will show it is wrong by increasing its objective value. Okay, so the optimal output is different. K is that index. Now up to k minus 1, it's exactly the same as alpha, so it's all ones. Except at the kth, it's kind of less than 1. Beta k is less than 1. Now what does that mean? Now again, there's actually another case within this. Maybe there is a k prime which has something more. So what we're going to do is we're going to replace. We're going to say, let's take away something from this item and put it into this kth item and show that the value can be increased. Okay, so how much are we going to take away? We're going to take away delta. Why am I saying delta? Because maybe you can't take everything away. Because if you took everything away and you try to put it here, you might go beyond 1. So you have to be careful. So let's take a little bit away and put a little bit over there. So choose some delta greater than 0. So if the delta is less than or equal to beta k, such that if I look at the weight of the things I take away, divided by the weight of what I'm putting it in, so this is the fraction that I'm going to put back in, that fraction is less than 1 minus beta k, which is whatever is left in k. 1 minus beta k is what's left. So I'm going to add that now to k, and I'm going to take away delta from k prime. I have a new solution. All the others are the same. Now, when I have this new solution, if I can show that it satisfies the knapsack constraint, and it has an optimal, and the value is larger, strictly larger, I get my contradiction. So I'm going to actually right? This is case 1a. 1a is suppose there is a k prime greater than k, okay? All right, so now let's just look at what is the total weight. So the total weight, remember that everything is the same for k, L not equal to kk prime. So I'll just say for all L not equal to k prime, it's the same as beta plus, or I'll say the new total weight. The new is of this new solution is beta k star wk plus beta k prime star wk prime. Okay, so this I can keep. Now I plug these expressions in. I'll get beta k wk plus delta wk prime divided by wk times wk, because I multiply this by wk, plus I get beta k, because I plug in this expression here, beta k prime wk prime minus delta times wk prime. Observe that this and this are just the same, right? Because the wk is going to cancel out with this wk. So these things are the same, and hence this is exactly the old total weight, which is again equal to w. Okay, so it's the same thing. Now let's look at the new objective value. What is the new objective value? So this is for kk prime. You just got whatever you had before. It's beta L times the value of L plus beta star k, value of k, plus beta star k prime, value of k prime. Just moving things over here to make it easier to read. Beta L VL plus. Okay, so now we get beta k vk plus. Now this is the key, right? So I added this amount of, I added this much delta wk prime divided by wk times vk plus beta k prime vk prime minus delta vk prime. Where's the contradiction now? This is the old objective, right? So this is the old objective plus delta times wk prime divided by wk times vk minus vk prime. Where is the contradiction?
We use the fact that vk over wk is bigger than vk prime over wk prime.
Exactly. And why is that? That's because k prime is greater than k. We sorted. Right? So this is strictly greater than 0. And that's because vk divided by wk is greater than vk prime divided by wk prime. Which means the new objective is strictly greater than the old objective. Contradiction. So this is the essence of the greedy argument. right? I mean, intuitively, it's quite clear, right? You kind of take things away from the old one, put it in the new, from something ahead and put it in something earlier, because the earlier thing has a more value to weight ratio. But this is the mathematics you need to do to actually get that proof. Now, there are some more cases left, but it turns out the other cases are actually quite easy, and I will show you. Are there any questions about this? That's why I said the greedy coming up with the algorithm is easy, the analysis is more challenging.
So I have a question.
Yep.
So here you assume you only change 2 items, but what if there's 3 or 4? So you have to consider solution beta star.
You don't need to. All you need, so this is what is interesting. All you need to argue is as long as there is something else ahead, you can do a swap. And a little bit of a swap is enough. You don't, even if there are other items out there. So as long as you have some K prime, it is enough. You don't need many, and it doesn't get affected if there are many. You're taking all of these items. You want to argue, so greedy took all of K, right? Because alpha K is equal to 1. Optimal decided to take less. You want to argue if optimal decided to take anything ahead, then it made a bad choice because it could swap. So what is the next case going to say? It's saying, well, suppose all of these are 0. Right? Case 1b is suppose. So that means it means for all K prime greater than K, beta K is equal to 0. Then what?
Yeah, but I think you are assuming that items greater than K would have an optimal solution of choosing only one item.
No, I'm not assuming that at all. There is no assumption here other than the fact that the optimal is choosing something else. So you're saying, okay, what if the optimal didn't choose anything there? Is that what you're asking?
What if the optimal would need to choose more than one item?
More than one item here?
Yeah.
It's still enough. All you need is there exists. It could choose more. I don't care. Like maybe optimal is doing something like this. Is that your problem?
Yeah.
It doesn't matter. All I do is I take any item here, decrease that and add here. All I want to do is take away from an item that has less value per weight and add it to this one which has more value per weight. I'm not trying to come up with the optimal. I'm just trying to argue the optimal made a bad choice. How do I argue that? Just by showing that I can increase the objective. And that is enough to show that it is not optimal.
Oh.
Right? Does that make sense?
Yeah. So you can actually write a summation over K prime, or if there are more than one K prime. Would that be more formal? Or?
No, it's not more formal. It would only make your math more complicated without seeming. How would it make it more formal? So so where is the informality here? Maybe this is trying to understand, like, what is the part over here that you find is not precise? It's just suppose there is some K prime such that that happens. Then you just have a choice. Now, what you might say is, suppose there was no K prime. That you're right. That's another case, and we will answer that shortly. That's actually going to be quite easy.
Okay, I'll think about it.
Okay, all right.
Thank you.
Okay, so case 1b is going to be much more easier. So suppose for all K prime greater than K, beta K prime is equal to 0. Okay, so so you don't have anything here. All of this is 0. Okay, now what is the proof?
Wait.
Yeah?
I don't think it should be that they're equal to 0. It should be that they're like.
No, I'm just taking the negation of this case.
Yeah, but there maybe. I think that there should be some. The first case should be that there should be some k prime greater than or equal to greater than I, right?
So, okay, so
like the if
go on.
I'm saying like if the optimal solution is like close to the solution that the algorithm came up with, but differs by one thing, it would be like there's some k in less than I, such that that's less than 1, and then some k prime greater than I. I don't understand, like.
Okay, good. So this is something that I did not specify here, and I was going to do it through this, but what you're saying is assume that the optimal also takes a total weight of W, which makes sense. Therefore, there must be a coordinate where it's actually strictly smaller, and there must be a coordinate where it's strictly larger.
Okay, I think I understand now.
Right? So you could do it that way, or what you could do it is you could do it this way. Both of them are equally valid. But as I guess someone pointed out in the comments, it means in this case we're taking less than max weight, so we know it's not optimal. And that same thing is going to happen in case 2. So there are multiple ways of doing this. Suppose for all k prime greater than k, beta k prime is equal to 0. Well, then what you do is the total weight is going to be the summation of beta, what is the index I'm using? J, beta j less than k, beta j, wj plus, plus beta k, wk, and everything else is 0. Well, then the whole point is that the weight chosen over here, now remember that all of these are just 1. So this is just going to be the summation of j less than k of wj plus beta k wk. And because you have this inequality here, beta k is strictly smaller than 1. And you know that k is less than I. This weight is going to be strictly less than j less than I wj plus alpha I wi, which is equal to w. And this is a contradiction, because the optimal should fill the knapsack. And so the same argument holds in case 2. In case 2, we said k is less than I. When k is greater than or equal to I, we'll get exactly the same situation. I think maybe what was pointed out earlier is you can say that maybe a different way of putting it, which would also give equivalent math, is that there must be an index where beta of whatever k is less than or equal to alpha somewhere in here. Is that your comment?
Yeah, but I think I've figured out that you don't actually care.
I mean, yeah, you could do it either way. You could do it, and so if k is greater than or equal to I, again you can make sort of similar arguments. I won't go through all of them in gory detail, but essentially using this you can complete the proof. The whole point is this math that I did here. I will say that there is another way of doing this which might be a little cleaner now in hindsight, now that I look at this, which is just to assume the following. So I'll just draw this over here. I'll say here is alpha, right? And this was your coordinate I. here is beta. And remember we said that summation wj, j less than I, plus alpha I, wi is equal to 1. We have summation beta of, whatever, over all j, beta j, wj is equal to w. So because both these weights are the same, and everything here is 0. So in this setting somewhere, there exists a k such that beta k is less than alpha k, and there exists a k prime such that beta k prime is greater than alpha k prime, right? Because just by balance, there has to be something here that is less, something here that is more, because it cannot be more over here, because that's the total weight. And so if you just look at this, this is enough to do whatever argument we did. This may have been a cleaner way of doing it, so I apologize. I mean, then that would have avoided some of the cases that I had written. This would probably be easier. There's a k here, which is going to be less, and there's a k prime here, which is going to be more, and again, you can now do that swap. The moment you have that sort of a situation, you remove something from here, and then you add it over there. And then you get exactly the same math, and you argue that the optimum could be improved, which is a contradiction. Any questions about what I've done so far?
Couldn't the optimal solution, I mean, no, but couldn't the optimal solution like have a little bit less in one of the first things and have a little bit more on index I, because we may not have filled it up totally?
A little bit less on one of these and a little bit more in here. Yeah, okay, no, you're right. So I think that this would have to overlap with that. There's this overlap here, like, so in this regime, there is, okay, so what you should say is there is a k and a k prime where k prime is greater than k such that these conditions hold. And that's enough. That's enough, right? The fact that where it is with regard to I, yeah, you're right. You could have something less over here and something a little bit more over there. You're right. I should have actually maybe drawn that boundary over here, but still you have this issue of the overlap. Yeah. I mean, it's at some level, basically, this is like a linear function. So whenever you have linear functions, you do what's greedy, right? You basically pick up the coefficients that are the largest and try to maximize your weights over there. Okay, any questions about this? All right. I did not expect to be spending as much time on this, but I think partly that's because maybe I did not polish this proof as much as I should have. So let me give you another example of a greedy algorithm. I will likely not be able to finish the analysis today, but it's a very classic example that you should know, and this is called Huffman coding. Historical comment is the inventor of Huffman coding. Huffman was actually a professor at UC Santa Cruz. I believe he may have been the founder of the UC Santa Cruz computer science department. So it's all the more important for us to talk about Huffman coding at UC Santa Cruz. Okay, so what is the question? And this is similar to what we had, what we discussed about optimal binary search trees last time. It's related to that. So in Huffman coding, so let's again, is to find the most optimal or the best, find the optimal prefix free encoding for a universe sigma given frequencies of elements in sigma. So for convenience, let sigma just go from 1 to n. And so the frequencies, this is just some array that maps every universe item, that just tells you how often a particular item exists. So you could think of this being just like the frequencies of characters. Now we want to design a binary encoding and we want a prefix-free binary encoding, which basically takes, we want the encoding, so I'll refer to the encoding as the encoding function E, which takes sigma, and this means binary strings. So this is binary strings. And moreover, what you want is no encoding should be a prefix of another. So the benefit of that is the decoding process is easy. So for example, if you had just the word encode, and if you had a prefix-free encoding, so let's just say that E was encoded with 0, 1, then N should not start with a 0, 1. So the encoding for N might be, so I don't know, E is 0, 1, N maybe something like 1, 1, 0, and then C, we would take something that is, so that we could take, let's see if that works, 1, 0, so C would be 1, 0. O is a bad symbol, so I'll just do O. O may be 1, 1, 1, 1. D, which we don't want this to be a prefix of anything, that could be 1, 1, 1, 0. And E is 0, 1. So note that if you wanted to decode it, it's really easy because you know that when you start from here, as soon as you start reading this and you get a 0, 1, you can stop right there because you know that it's not going to be a prefix of any other code. So you read off 0, 1, you start reading from here 1, 1, 0, and you can stop. And if you start reading, you go 1, 0, oh, there's nothing else that matches, so on and so forth. Right? So the decoding process is automatic. Does this make sense? The decoding process of a prefix-free code is easy, and that's why you want a prefix-free code. Now, another way of representing a prefix-free code, is a binary tree. So you start at the root, and you say going left is a 0, and going right is a 1. So you took a 0, you took a 1, and this is E. You take a 1, you take a 0, and this gives you C. 1, 1, 0, that gives you 1, 1, 0 is an N. It's an N, and then 1, 1, 1, 0, 1, and so finally this gives a D, that's an O. Right? So you see how this is basically the leaves of a binary search tree. The leaves are the characters, and the path is the encoding. And this is automatically prefix-free because the leaf has no children. So the prefix-free codes and binary trees are basically, they're one and the same thing. This now gives us a convenient way of understanding the encoding process. Any questions about this? Is this clear? I'll just pause. I will poll you. Is this clear? A is yes, B is no. Okay. Very good. Actually, maybe I should ask a question. How many of you have already seen Huffman Coding before? A is I've seen it. B is I've seen it, but I would like to see it. And C is I don't know what Huffman Coding is. So again, A is I've seen it and I know it. B is, I've seen it, but I'd like to see it again. C is I have not seen Huffman Coding. Okay, good. So many of you are in the B or C boat, which means that there's some utility to me talking about this. And okay, so now we have a prefix-free code, which is a binary tree. So let's just think about the encoding can be thought of really as building a tree. So encoding, the encoding is a binary tree with the characters, or basically the universe, as leaves. Okay? And now, just like we saw before, there's this notion of what is the length of the total encoding is we sum over all characters. We look at the frequency of the character. So I'll just think of that as a function. The frequency of the character times the depth of the character. So this is the depth of I in the binary tree, which is also the same thing as the length of the encoding. Right? Because if you go back and look at this picture here, the length of the encoding is the depth. The length of the encoding of E is 2. The length of the encoding of N is 3. The length of the encoding of D is 4. So this is the length of the encoding. And so now we have our problem is compute the encoding tree that minimizes the length of the total encoding. Right? The length of the total encoding is the frequency times the depth. And so naturally what you want to do is to have frequent items being higher up, having a lower depth, and infrequent items having a longer depth. Remember that you can always encode in such a way that you have log of the length of the universe, log of the size of the universe, because you could just do everything. You could imagine that the tree is simply a balanced binary tree. So the number of leaves is going to be the number of characters. The depth will be the log of the number of characters. So all characters are encoded with, the same, which you can think of almost like an ASCII encoding, where all characters essentially have an 8-bit representation, so that's all prefix-free automatically. But that is not the most efficient encoding, because in this case, it might be worth having a letter like E being infrequent, E being frequent, having a smaller representation, versus maybe, well, in this case, all of these letters are fairly common, but if you had a letter like Z or X, you may want to make it much longer because it is infrequent. You may want to place it at a higher depth, and so your tree might be imbalanced. There is a benefit to imbalance. And so the problem that we have here is to compute the encoding tree that minimizes the length of the total encoding. Any questions about this? Any questions? All right. And so essentially, the point is there is a very simple and elegant greedy algorithm that comes up with the optimal encoding. And it's kind of interesting because your natural instinct is to say, oh, I'm just going to take the most frequent character and make it have the lowest depth. And actually, that's not the optimal decision to make. So you have to think a little bit differently about it. But the algorithm in the end is going to be greedy. Now note that there is an optimal substructure here, just like there's an optimal substructure to any of the problems we discussed. Like in Knapsack, you can also think of it as once you pick an item, then you have a new knapsack problem which you need to solve. So similarly, one can think of Huffman coding as, one will try to think of it in terms of an optimal substructure. So I'll just write out the idea of the main idea. I will go over this again in the next lecture, although I will not go over the whole description of Huffman coding. So please look over that before you come for the next lecture. So the idea, which is really clever, is the following. So it's take the two most infrequent characters, make them siblings in E. So I will, somewhat abusing notation, when I refer to the encoding E, I'm actually going to think of it as a binary tree. So we are going to make them siblings in the binary tree. So which means if we take the two most infrequent, we know that they're going to be siblings of something, but we don't know what the remaining tree is going to be. So to solve the remaining tree, we'll just do it recursively. We'll say combine the characters. Combine the characters to get a new character, sort of a new character with the total frequency. So we imagine that there is a new character here which has the total frequency of these two, and then we just solve recursively. So we imagine this is a character with a new frequency, and then we just solve recursively. That is now going to find the two most infrequent characters in whatever remains, which may be this character, but it might not be that. And then those will then get sort of combined to make something, and things get combined, so on and so forth. And as this process builds and solve recursively, and we'll just say that the two most infrequent characters, I'll refer to them as I and j. And I'm just saying make I and j children of the new character. Right, so we got this new character, so we have a tree where the new character is the leaf, and so you make these children of that new character. So this is the idea of Huffman coding. And it's a greedy algorithm because you simply just take the two most infrequent characters. This is the greedy part. You don't need to do dynamic programming here, so this is very efficient. And this gives essentially, using a priority queue, this is also a classic use of a priority queue, like a binary heap. One can essentially, in n log n time, construct the optimal encoding tree. So I'll end here. In the next lecture, I'll talk about the algorithm in more detail. I'll give a proof of correctness, and we'll talk about some more greedy algorithms.